Oh yeah, this is working great. Can you see the slides changing, or do you only see the front of the slides?
Yeah.
Yes, we can see the slide changing.
Oh, perfect. Okay. So yeah, today I want to tell you about a recent work that I did with Stacey, and it's called Multidimensional Quantum Walks, and it's kind of a generalization of quantum random walks, of kind of the most general framework that we had up to this point. And I will first kind of briefly give a bit of context about our results, and then we'll dive a little bit deeper into the framework, what makes it new, kind of how does it work. And if there are any questions, please just interrupt me, because I want to see your, like, if I want to probably see if you're like raising a hand or something. So just shout and I'll stop and we can discuss. So okay, so we have kind of two main applications of this framework, and I'll want to briefly discuss the context of these results. And one of them is the problem of k-distinctness. So let me give a little bit of history. And k-distinctness is a generalization of element distinctness, which is probably more well known. So in the problem of element distinctness, we have a list of, say, n elements, and these elements are like polysized in n, which basically means that we can kind of efficiently write down all these elements in polylog time. And we have to judge or decide whether there are two elements in this list that are equal or not. So we have to decide if there are two indices in this list such that their elements are the same, or if they're actually all distinct. So that's where the name, like, element distinctness comes from. And this is a well-known problem in computer science, and classically there is not much better to do than just kind of checking everything and seeing if they're indeed all distinct or not. With quantum, this problem is way more interesting. So using amplitude amplification, one can show that we can actually improve on the classical case. So it's actually enough to not query everything, but only 3/4 and to the 3/4 of the input. And this was later actually improved by Ambinus to n to the 2/3. And it was shown that this was in fact optimal, I believe, with the polynomial method. So the problem of element distinctness is kind of very nice. So I will be using this. Okay, can you see my mouse on the screen? Can you see it's moving?
No, we can see your mouse.
Oh, you can't. Okay. Then, as you can see on some of these O's, I have this tilde, which means that we're suppressing polylog factors. So there might be polylog factors in the bound, but we kind of ignore them. But to show that they exist, we have this little tilde. So that means that kind of up to polylog factors, the time complexity is well established of this problem, and the query complexity is even tight. So we can generalize element distinctness to k-distinctness, where instead of deciding whether there are two elements that are the same in the list, we have to decide whether there are k elements the same in this list. So this is a considerably harder problem, because we could have that there are many kind of elements that form like k-1 collisions, but there might only be a single or even none of these that actually extend to a k collision. So classically, you still have to basically query everything. And quantumly, Ambinus showed back in the paper where he gave his element distinctness algorithm that you could kind of generalize this algorithm for k-distinctness. And note that this is kind of, as k is increasing, this becomes very close to just n. But it's important to note that we always consider k to be a constant. So for all these algorithms that, like in the history that I'm mentioning, but also in our algorithm, it really relies on the fact that k is constant, because otherwise the complexity will be horrible. So this was the previous work by Ambinus, and then Belovs in a very good paper, very interesting, showed this very kind of, it's a more odd bound. We even have like an exponential of 2 to the k in there in the fraction, and this proof, or this algorithm, wasn't constructive in a way. So it was really obtained from kind of a dual solution to the adversary bound, and there was some span program intuition in there. So even though he could prove how many queries the algorithm made, we have no idea what the time complexity is of this algorithm. So whether it's kind of, whether queries are really kind of the hardest thing that's going on there, or if there's a lot of other computations going on. And one could think intuitively that if you're dealing with such a list and you have to decide whether elements are equal or not, then querying is probably the only useful thing one can really do. So it makes sense from an intuition point of view that the time complexity should be the same as the query complexity, but there was no proof. So onto the lower bounds. Oh, my apologies. There's people could kind of make his algorithm or a slight variation on it constructive for the case where k is 3. So there were like separate independent works that gave a approach that kind of matches the bound from Bellows. So if in the more general bound of Bellows, if you would fill in k is 3, you would exactly get 5/7. But for larger than 3, people didn't really know. And in her PhD thesis, my supervisor Stacey managed to improve the upper bound from Ambinus in the more general case for time complexity. But as you can see, it's still not the same as the query upper bound by Bellows. So these are the upper bounds. The lower bounds are also getting very close to n to the 3/4, because as you can see in Bellows' query upper bound, if k becomes very large, then this really approaches n to the 3/4. This is the same for these lower bounds, but they don't converge as quickly because we don't have this exponential in the fraction. So if I would show you this graph, this is kind of, we have here mapped the query upper bound, the time upper bound, and the query lower bound. So green is the query lower bound, blue is the query upper bound, and red is the time upper bound. And of course, in the perfect world, these would all match and the problem would be resolved up to polylogarithmic factors. But there's quite a gap in there. And in our work, we actually managed to match Bellows' query upper bound with time. So in this picture, we managed to kind of push down this red line to make it match the blue line. Note that it's still an open question whether this is optimal, right? Because the lower bound is still, it isn't matching. So the question is, can we improve on our algorithm, or can we improve on our lower bound methods? This is one of the main applications of our framework. The other one is welded trees. So welded trees is a kind of a different problem. So our input is, we have an oracle, and we can query strings, and it will either tell us that the current string is not a valid vertex, or it will give us the neighbors of the current vertex. So this capital gamma, it will denote the neighbors of the current vertex u. So how does this graph look? We have two binary trees, and each binary tree has depth n. And in the middle, these trees are kind of glued or welded together in a random way, such that the degree of each vertex is 3, except for the start vertex and the end vertex. So each vertex is specified by a 2n bit string. But note that we have considerably fewer vertices than 2 to the 2n. So this means that with very high probability, if you just try a random bit string, it will not be an actual vertex. And our goal is that we start at S, and let's say that that's just the all 0 bit string. And our goal is to find T, so to find the bit string associated with the vertex T at the end. So that's what the algorithm will have to output. Classically, because such a negligible fraction of all bit strings actually corresponds to a vertex, there isn't much better to do than just kind of start at the beginning and just try to random walk yourself through this graph. And in the first half of the graph, so kind of in the left tree, this is okay because there are more vertices moving or more edges moving you to the middle of the graph than back to S. But especially once you pass the middle point, every vertex will have 2 edges moving you to the left and only 1 edge moving you to the right. So it turns out that you'll just have to kind of, for an exponentially long time, walk around this random walk until you're lucky enough to end up in T. But quantumly, and this problem was kind of created to show this exponential walk advantage. Because quantumly, in the same paper, Childs and his co-authors showed that you can in fact traverse this graph in a polynomial number of queries in the quantum sense. So the actual algorithm that they give, it's less of an actual random walk in the classical sense. It's not discrete. I believe they actually create a Hamiltonian kind of based on this graph structure, and then they just evolve this Hamiltonian, and that's the way they do it. So it's less of a random walk in the more classical intuitive sense, but nevertheless it's still a continuous time quantum walk. And this result has later been shown to kind of reduce the power of the polynomial. And in our work, we actually managed to show that it can be traversed linearly. And I think more importantly, because it's still polynomial time, we still have an exponential speedup, but we construct the random walk in a very kind of intuitive classical way. So there are no Hamiltonians going on. Personally, I don't have a physics background, so Hamiltonians kind of scare me. So it's nice to be able to construct the algorithm in a purely kind of classical intuitive way. So these are kind of our results in their context. And this is what I want to talk to you about today. So we'll start a little bit about random walks and quantum random walks. Then we'll discuss the electric networks framework by Bellows, which is a very nice, and it was up to our work, it was the most general kind of way to construct quantum random walks. And it's a framework with, I would say, quite a nice intuition. Then we try to apply this network to the welded trees problem and show that there's a slight problem why it wasn't applied to it before. There's kind of a point where it breaks down, where you cannot get this very nice exponential speed up. And then we show what our framework does to kind of fix this problem, and then how to fix the welded trees algorithm. So yeah, let's start with random walks. I won't go into the full kind of Markovian introduction of random walks. It's not as needed for our framework. So we'll just do the kind of nice intuitive picture of we're on a graph. And there are a couple of things that we have to be able to do in this graph. For any vertex, we have to kind of be able to sample a random neighbor, which would be kind of a random index in its degree. We then have to, from this index, be able to actually compute the neighbor. That will kind of move us from one vertex to the other. So the sampling of the index would be to kind of decide which edge do we want to take, and then the transition step would actually be to compute where does this edge take us, and then actually traverse this edge. And our goal is that some of the vertices on this graph are marked, which we denote by the set capital M. And one thing that it's kind of sounds trivial, but it's important to note, is we have to know whether we are in a marked set. So we also have to be able to, for any vertex, check if we're already there, if we manage to make it to the marked set, or if we still have to keep looking. And there will also be, we of course have to start somewhere on the graph, and this can just be a single vertex, but kind of the more general case is that we start with an initial distribution. So an initial distribution sigma on the vertices, which means that we need to be able to sample an initial point based on this distribution. And this distribution can be trivial in the sense that it can just be a single point. But usually in a quantum setting, this would kind of be a uniform distribution over a set of vertices, and that's where we start. And then a kind of an important notion in classical random walks is something that's called the hitting time. So the hitting time, that depends on sigma, because it kind of depends where we start, to on a certain graph G end up in in a marked set M. And classically, the complexity of such a random walk would be, first we have to set up our start state. So we have to be able to sample from this initial distribution. And then kind of we have to make a transition step and check whether we're in a marked vertex. And then we have to repeat this process for about the hitting time of the graph under sigma and M. So this is what happens in the classical setting. And quantumly, one can improve on this. So kind of what happens when we enter the picture of quantum random walks? Well, starting with the setup, if classically you would sample according to sigma, quantum, there's this kind of very nice thing. What you can do is you can just take a uniform superposition scaled by sigma. So now you can, of course, by just measuring, you have sampled from sigma, but you can also not measure and keep the superposition and kind of keep that power in the algorithm. So kind of similarly, instead of sampling a neighbor from a list of neighbors of a vertex, we'll do the same kind of thing. So we'll instead kind of create a superposition over possible neighboring edges. And here this W, it's a weight function, because sometimes you want to have a kind of a nice uniform superposition over neighbors, but sometimes you might know that a certain edge is probably a better choice than another one. So you can kind of scale this choice by a weight function. Now these weights are not necessarily normalized. So here's why I denoted kind of the proportional to, because one would still have to kind of normalize this whole thing to be a state. And then how does this change in the complexity of the walk? So what happens is we actually get a square root of something else. So it's not the hitting time, it's something else. And for those familiar with random walks, this is referred to as the commuting time from sigma to M. Because I mean, we're in a quantum setting, so everything has to be reversible. So it's kind of not only takes into account how fast or how many steps we have to take to move from the initial sigma distribution to a marked set M, but also back. And this is referred to as the commuting time. But it's still kind of a more vague notion. The hitting time is a bit more intuitive. So if one would kind of create such a quantum random walk, it would be quite hard to analyze what this commuting time actually is and how to analyze it and to properly analyze the complexity of the algorithm. And this is where very nicely the framework by Bellows comes in. So in the electric networks framework of Bellows, we'll consider our graph to be bipartite. This is an assumption that one can easily make. One could, for instance, always kind of for every edge put a vertex in between the edge, and then one has created a bipartite graph. So for now, we'll just assume the graph to be bipartite, and this bipartiteness is kind of emphasized here with the different colorings. So as you can see, there is no edge going from any vertex in a blue set to another vertex in a blue set. And the marked set, we've only put it in the last layer, and we have emphasized it with the color red. So those are the marked vertices. And what we're going to do is, as you can see, this graph, maybe it's not very clear, but there are arrows. So all the edges are kind of going from left to right. This is an arbitrary direction. And in fact, the walk that we will be doing is on an undirected graph, which is very important in a quantum way, because you want to be able to kind of reverse, take the inverse of a step. So that would be very hard if the graph was directional. But the directions we just put in there for the goal of creating a Hilbert space. So we'll create an Hilbert space on the edges of the graph. So every basis state is an edge. And so every edge could be represented by a state. And the reason why we consider a direction on the Hilbert space is because then something very nice happens. We could also consider the edge in the other direction. And we say that that's in fact a negation of the original state. So if we instead defined the Hilbert space on kind of the undirected graph, then this would happen. So we just choose an arbitrary direction. And now what you can do, because now we have put the edges in a linear algebra framework, so we can just add these edges and we actually obtain 0. So this is kind of a nice, more intuitive way of looking at the graph. So now we have a Hilbert space. So what does the framework actually do? We give the graph an extra kind of initial vertex v0, and we connect it to everything in the first layer, and we only connect it to the marked vertices at the end. So now we have a very kind of, if there are any marked vertices, we have a very nice kind of cycle going through the whole graph. So you can start in V1, kind of traverse through the marked vertices, and then go back up to V0. Another important state related to this graph will be kind of this initial state. So it's all the edges that are coming out of V0 and that are going into the first layer of our graph. And remember, we're considering the decision problem whether the graph has any marked vertices or not. So we will not be interested in deciding whether, like, what is the marked vertex, but we just have to decide whether this graph has any marked vertices or not. So we kind of have two cases, decide whether M is non-empty or decide whether M is actually empty. And the way that the electric networks framework does this is, in the non-empty case, we're trying to find some state theta. And note that I will not necessarily assume that our states are normalized. So it's not necessarily the case that theta is normalized. And we want this theta to have a non-zero overlap with our initial state. But it has to be in the +1 eigenspace of some unitary U that we have not defined yet. And we'll do that shortly. So in words, we have that psi0 needs to have non-zero overlap, namely with theta, which is in the +1 eigenspace of U. Well, we're doing a decision problem. So if this would correspond to M being non-empty, then the M is empty case would be precisely the converse. So psi0 would have 0 overlap with the +1 eigenspace of U. And for those familiar with quantum algorithms, if you have to decide which of these cases is happening, you can do phase estimation of U on psi0. And you could decide up to some accuracy, of course, because if you could just run it up to infinite accuracy, you could decide it perfectly. So there should be some epsilons and deltas in this definition, but for clarity, I've removed them. So with phase estimation, one could decide which of these cases is true. And we're going to make life a little bit easier. So I will create some spaces A and B, such that theta would either be in the complement of the union of A and B. So here, A and B are kind of our linear subspaces of our Hilbert space, and this plus means I will just take the span of those two things. So I can have a vector in A, a vector in B. I can have a vector that's both in A and B. So either theta is in the orthogonal complement of the span of A and B, or in the other case, we have that psi0 is actually in the span of A and B, and also that psi0 is not in B. Now, this seems very arbitrary, and there doesn't seem to be any intuition why we would do this. But there is a very important reason to kind of define these spaces A and B as this, because now we can actually create a unitary that depends on A and B. Namely, we choose the projection, or sorry, the reflection through B and the reflection through A. And now we see that if theta is actually in the orthogonal complement of A and B, that means that the first reflection through B will give you a minus sign because you're in the orthogonal complement of B. And then the reflection through A will give you another minus sign because you're also in the orthogonal complement of A, meaning that theta is actually in the +1 eigenspace of U, because we get a -1 from the first reflection and then another -1 from the second reflection. But if psi 0 is actually in the span of A and B, but also orthogonal to B, then the first reflection will give us a minus sign. And then the second reflection will not do anything because we're in the span of A and B. So it might, so not do anything is not completely correct. It might move us a little bit, but it will definitely not give us another -1. And hence psi 0 will have 0 overlap with the +1 eigenspace of U in this case. We're now going to kind of construct these spaces A and B such that it's easy to analyze this phase estimation algorithm. So note what we're doing here, and this is really, I find really cool about the electric networks framework, is that a quantum random walk is just phase estimation. But then, of course, we kind of move the difficulty from analyzing the random walk to analyzing a phase estimation algorithm. But because it's still so closely related to this graph, we'll be able to kind of use classical random walk intuition to analyze this phase estimation algorithm. And a key element of creating these spaces A and B are something that we call star states. So if we zoom in on a single vertex in this graph, let's say U in the second layer, we can consider the state that's the kind of the sum of all these edges coming out of U. So this is the star state of U, and note that all edges have some weights attributed to them. So here you see the definition of the star state. And we said that the graph was bipartite. So like one part of the vertices is labeled by a set A, and one side of the vertices is labeled by a set B. I'll apologize for the notation here because A and B are both kind of linear subspaces of the Hilbert space, but they're now also denoting subsets of the vertices. And the span of all star states of the graph is exactly the star states of A and the span of the star states of B. And these will be.
Sorry.
Oh, yes.
I have a question. So is this vertices U on the right that have 4 arrows outside of the vertices? Is it supposed to be the same U from the left-hand side where you have 4 layers?
Yes, it's the same, but note that we have changed the direction of some of the edges, right?
Yeah, right. So you do that deliberately, like you. Okay, I see.
Yeah.
Okay, good.
Yeah.
Thanks.
So the star states will always consider the edges kind of spreading out of the vertex, like a star coming out of the vertex.
Okay.
So this means that indeed sometimes it will not match the direction of the edges that we have kind of created in the graph. Mm-hmm. So this could mean that there are some minuses in there. In the star state. Yeah.
So whenever the direction are different, then you would have a minus phase, like you have a minus. Okay. Okay. Exactly. Cool. Thanks.
Yeah. Thanks. So this would mean that kind of in the definition you have like the ket EUV, and this ket EUV could also be minus ket EVU.
Okay.
And then indeed, yeah. And so these two, kind of the span of the start states, they will be precisely our A and our B. So our unitary U will be the reflection through one of these sets of star states and the reflection through the other set of star states. And maybe important to note, because it's a bipartite graph, any 2 star states in A, they will have non-zero, or they will have 0 overlap, because there is never an edge between any 2 vertices in A. So that means that any 2 star states in A, they have 0 overlap. And that means that if you want to reflect through A, it's actually enough to just reflect through every star state in A. And then you will have done the reflection. And if you want to reflect through B, you can just reflect through every star state in B. But one thing that's important to note is that A and B are definitely not orthogonal. because every star state in A, kind of every edge coming out of A, it's also an incoming edge of B. So there's actually a lot of overlap between these spaces. So let's see what we've wrote in the green part. We said that we are looking for some vector theta that's orthogonal to A and B. So we are looking something that's orthogonal to all star states. So what is orthogonal to a star state? Well, let's try to find out. So here we have a star state. And let's say that we consider kind of an edge going into U and an edge going out of U. Well, okay, we can compute this inner product. So on one part, the edge directions match up, so we get a 1. But on the other side, the edge directions don't add up, so we get a -1. So hence, this inner product is 0. We can even add some edges that don't coincide with the star state at all. It will still be 0 because we're just adding a 0 overlap. So what we can also do is we can now kind of add these things together and we get a cycle. And note that every cycle is precisely orthogonal to a star state that it's in the cycle, because there will be one edge going in, which will be the other direction of the star state, because the star state is always going out. So we'll have a -1 there. And then we have one edge going out of the star state again, which is precisely the same direction of the star state, and that will give us a +1. So we can have 0 overlap, or an inner product of 0 with any star state that's in the cycle. So it's not only for U1, but it would also be for U3. But more importantly, it would also be for any star state that's not part of the cycle, because there's just no overlap at all. So it turns out that such a nice cycle is in fact orthogonal to every possible star state. And then by linearity, we can also just take linear combinations of cycles. And these things we'll call circulations. So circulations on G are precisely orthogonal to our star states. Let's kind of properly define such a circulation. It's a linear combination of cycles, which means that it's a real valued function on the directional edges that satisfies kind of we'll also call this a flow. So the flow along one edge is precisely the same as the negative of the flow going the same edge but the reverse direction. And we'll need, because it's a combination of cycles, that all the flow going into a vertex is the same as all the flow coming out of a vertex. So if we add all the flow in a single vertex along all its edges, it should be 0. I think a picture is more interesting in this case. So this would be a flow. We're having some flow coming into the vertex, totaling up to 2/3. And then we have flow coming out of the vertex again, also totaling up 2/3. But maybe we want to reverse edge directions, and that's fine. And then we can just have negative flow along the edge directions. So now there is still 2/3 of flow coming into the vertex, and then we have another 2/3 of flow coming out of the vertex. Or you can also see it as 0 flow coming in and 0 flow coming out. So these kind of nice intuitive flow things, we can kind of see it as we have like a water faucet, and we connect it to our graph, and we're just running water through our graph. And this would be a flow, and this is precisely orthogonal to our star states. So let's kind of remind what we've seen so far. We have a graph. We kind of gave it some initial vertex V0. We have our two spaces that are obtained by the span of all star states. And we're going to, and we have some initial states. And first we had to find a state theta that's orthogonal to all star states that has a non-zero overlap with our initial state. Well, we just saw what was orthogonal to all star states, namely flow. So we're just going to send flow through this graph. So like I said, you're going to put some water into it, and it's going to very nicely flow through this graph. And as you can see, psi 0 actually has a non-zero overlap with this flow, because there's some flow going out of V0 into V1, and that would exactly be the overlap with the state psi 0. So okay, we have found a theta. So now let's go to the other case. In the other case, we had to show that psi 0 is in the span of A and B, and that's orthogonal to B. And here I'm going to kind of quickly prove this with pictures. So we can take kind of the sum of all star states in A. And so here I've just added all star states in A. And I'm going to add to this all star states in B. And because there's no, there are no marked vertices, there's no edge coming kind of out of the end of M back into our initial state again. So it kind of stops at the last layer. And now if you're going to add up all these edges, note that like the directions are reversed. So they're all very nicely going to cancel out. And we'll only be left with the edges going into V0. And this is exactly kind of psi 0 with the directions reversed. So in fact, psi 0 is in the span of A and B. And as you can also see, it has a non-zero overlap, or sorry, it has a 0 overlap with all the star states in B, because it only matches some star states in A at the beginning, but there is no overlap with things coming out of the red part. So these are actually the elements of our phase estimation algorithm. So now one can just kind of run phase estimation on this U and actually decide whether there are marked vertices or not. And in practice, this means if you want to create such an algorithm using this electric network framework, you would have to create a weighted graph G, or actually G prime, and find a flow theta. So you create a weighted graph G, you create a circulation or a flow theta, and how expensive is this? What is the complexity of such an algorithm? Well, first you have to generate your initial state, which is kind of all these edges coming out of V0 into the first layer of your graph. We're going to do phase estimation on the unitary U. So you have to be able to generate this U. And because it's the product of reflections, where these reflections are just the star states, the cost of generating U is just the same as generating these star states. So as long as we can generate these star states, we're happy. And this is kind of intuitively, this makes sense, because such a star state is just a superposition over neighbors. And that's exactly what you would expect from a quantum random walk. You're in any vertex and you're just going to take a superposition over neighbors, and that's how you transition the random walk. So now the question is, how often do you have to do this? Kind of what is how often do you have to run this phase estimation step? And this depends on something that's called the effective resistance. And the effective resistance is upper bounded by the energy of the circulation. So this would be the norm of theta, of our vector theta. And maybe a more physics intuition is you can kind of consider all the edges in our graph to be pipes. And the width of the pipe, that's denoted by the weight. And then we're sending theta of flow into this pipe. And that's going to create energy. There's going to be like water rushing through these pipes. So clearly, if we put more flow into it, there's more energy. But also, if we kind of make the pipes smaller, there's going to be more pressure buildup into the pipes. So that's why this energy of the circulation kind of scales this way with theta and W. But now you would say, well, I can just make the complexity very small by just making W very big. But you cannot have all nice things in life. So sadly, we also have to, the weight of the graph is also involved in the complexity. So this means that when you actually make such an algorithm, there is some kind of trade-off between the weight of the graph. So you want to kind of somehow weight your edges in a way that the energy of the circulation is not too large, but you also have to keep in mind that the weight of the graph doesn't become too large. So there's this very niche trade-off. And so this is actually how these kind of quantum random walks work. And such algorithms have been applied to problems. And it makes sense to try to apply this to the welded trees problem. So let's see if we kind of can create this kind of flowing through the welded streets problem. So let's remember our graph. So we have this binary tree of depth n, and we weld it to another binary tree of depth n. And these numbers below, those are specifying the number of edges in each layer. So I'm not really counting up to n, I just kind of stopped at 16 and then I go back again. So for the complexity of the phase estimation algorithm, we need two things. We need the weight of the graph, which is just the sum of all weights of all edges. And we need to upper bound the energy of the graph. So we have to create a flow that's going through this graph. Okay, so let's start with a flow. I would say a very natural flow through this graph would be just to split it. So there's one flow coming into S, then we split it, so there's half flow going along each edge, and then we split that flow again, and then we split that flow again, and we keep going like that. And then, of course, once it gets to the right hand of the graph, these flows are adding up again. So at the end of the graph, you will have like, at the very end of T, there will be like 1/2 of flow coming in from the top and 1/2 of flow coming in from the right. And let's say that we don't like weights, so we can just set every weight to 1. So what happens, then the weight of the graph would actually just be the number of edges, and that's exponential. So this is the case where we set every weight to 1. But the flow, if we calculate it, it's actually very nice because we get like a half plus a quarter plus 8. So that's just constant. It would be like 4, I believe, or upper bounded by 4. So okay, so maybe our weights are quite heavy in this instance, but the energy of our flow is definitely very low. So if we plug this in the formula, turns out that usually this setup is kind of negligible, and the C is also not very important. So this basically kind of scales with the square root of the energy and the weight. But that's bad. That's still kind of too big. So we haven't really set the right weights for our graph. So usually you want to kind of balance it in such a way that R and W are in fact the same. So let's try that. So we could kind of let the weights scale with the flow. So we set the weights on the first edges by 1/2. Then in the second layer, all edges have weight 1/4, and then 1/8, and then 1/16, etc. Again, this seems like I would say a natural choice of weights for our graph. So let's see what changes. The first part will just be linear, because first we have 2 edges, each of weight 1/2. Then we have 4 edges, each of weight 1/4. Then we have 8 edges, each of weight 1/8. So if you add all this up, it just scales linearly with n, with the depth of the whole graph. So okay, it's not exponential anymore, so that's definitely some progress. And if we now compute the energy, so we have to divide by the weights, and then we see that we get exactly the same expression. We again get 2 times 1/2 plus 4 times 1/4 plus 8 times 1/8, etc. So this also scales linearly with n. So that's actually very nice, because now if you compute this, the complexity of our phase estimation, it's ON. So it seems like we might be done. But remember that I said to be able to run the phase estimation of U, so to be able to run these reflections, you have to be able to create the star state. So what does a star state look like in this tree? Well, let's consider such a star state. So the star state was kind of the weighted edges coming out of such a vertex, which means that it will be proportional to some parent. So the P of X will be kind of the parent of U. And then we have like one child and another child. And the childs, they have a smaller weight than the parent. But this is very hard to create. We cannot generate the state, because for any vertex in the graph, we do not know what its parent is. We do not know what is left or what is right. Because if we knew this, it would be very easy to just walk along this graph. You would just always move to the right. But we don't know. So we cannot generate the star state. Kind of, if you could generate the star state, you could just walk around the graph in a very trivial way. So we cannot run the phase estimation algorithm like this because we cannot generate the state, because we do not know what the parent of a vertex is and what its children are. I mean, in the beginning of the algorithm, it could be kind of more simple because you could kind of save where you have just been, and where you have just been would be the parent. But once you get to the right part of the graph, this whole breaks down because you haven't been to the parent yet, and you cannot generate these states. So that's actually a shame, because up to this point, the welded trees went so well with their energy and our weights, but it kind of breaks down here. And this is where our framework kind of comes in and tries to resolve this issue. So we now move on to actual multidimensional quantum walks. So how do we resolve this problem? So remember, to be able to generate this reflection, or this product of reflections, we had to be able to generate a star state. But we just saw with the welded trees that actually creating the right star state can be very difficult. So we're going to change this a bit. Instead of generating a star state, we're going to be generating some linear subspace, capital psi. And it cannot just be any linear subspace. So we're also going to alter the definitions of A and B. So before we had like that A and B were the span of these star states. Now we're going to be the span of these linear kind of star spaces. And first of all, such a linear star space has to be in the span of actual edges. So it has to be the span of like proper edges in our graph. And second of all, our original star state must be in this linear space. So kind of the good option has to be there. And I would say an intuitive explanation of what's going on is that this star space is spanned by a lot of star states, each for maybe kind of a different neighborhood of you. So you're choosing to only take some of its neighbors, or you're choosing to kind of change the weights of these neighbors. But that's kind of the first line, so that the star space must be a subset of kind of all proper edges. And the second part means that the actual star state is in this set of potential star states. So first of all, it makes it easier because we don't have to create the actual star state. We just have to say, well, the actual star state is one of these possibilities. We don't know which one, but it's definitely one of these possibilities. And that's easy, right? You don't have to find the correct solution. You just have to give you a list of possible solutions. There's one problem, however, because remember that we needed our flow to be orthogonal to all star states. Well, now it will have to be orthogonal to a star space, which is way bigger. So it not only has to be orthogonal to a star state, but it also has to be orthogonal to all these like kind of alternative star states that we create that span this space. So on the one hand, we make it a little bit easier, but we also add difficulty. If we could only make it easier, then that would be the dream, but sadly, it doesn't work like that. So to give another kind of picture of what's going on, so in multidimensional quantum walks, we have some graph with vertices. And what we used to do is for each vertex, we would just create a star state. But now instead of creating star states, we're going to be creating star spaces for each vertex. And this we call alternative neighborhoods. And it's kind of one of the two main things how our framework improves on the electric network framework. Now it does one more thing that we won't need for welded trees, but it's actually something that's needed in K-distinctness. And it's also used in a recent paper by Stacey on variational time quantum walks. And that is, say that we have made these very nice alternative neighborhoods, but what if one edge has a very expensive cost like capital T? So maybe all other edges are trivial to walk around, but one edge is very expensive. Then before, what you would have to do is you would sadly just multiply the cost of the whole algorithm by capital T. You would just have to kind of incur this big cost on this one edge on every edge. And what we actually show is that if you have an expensive edge, and what I mean with expensive edge is say that it's not just querying a neighbor, but maybe this edge means that you have to run Grover search to actually find a neighbor. Then that, of course, doesn't have a trivial cost of one query, but it would be square root of n of queries. Maybe it would be a slightly smarter search, but still it would be a non-trivial step to take in your graph. And so then we just kind of split this edge into multiple edges such that each edge is still a trivial step. And then you would have like capital T of these steps. And this is something that we call edge composition. And we have some applications of this. But for now, you may forget it because it's not important for welded trees, and we can solve it just with the alternative neighborhoods. So how do the alternative neighborhoods help us here? Well, let's go back to the welded trees graph and remember that we cannot generate this state because we just don't know what its parent is. So how are we going to solve this? We're going to create a star space, which is just spanned by all three possibilities. So for any vertex u, we're kind of going to list all its neighbors by u1, u2, u3, and we're going to just consider all three possibilities. So either u1 is the parent, or u2 is the parent, or u3 is the parent. And we definitely know that the correct star state is in this set. So we're very happy. We can generate this, and we have found a star space. But remember, that was the easy part. Just creating more options is nice, but it's not yet orthogonal to the circulation. But luckily for us, we can just kind of modify the weights of this graph in a very small way, such that we can still make it orthogonal to the flow. So I'll show this first. So first I will show why it's not yet orthogonal to the circulation theta. So let's consider the flow that's kind of going into this vertex. So we have one part of flow coming in through the parent, and then we have a half flow going out of each of the children. And then we still have to scale this with the weights. So note that the weights of the children are half the size of the weight of the parent. So that means that our flow is actually proportional to the following state. Okay, and now consider our alternative star states. And for now, I'll just assume without loss of generality that the parent is U1 and that the children are U2 and U3. So this will just change into this. And now let's consider our star states. So we have these three kind of possibilities in our star space. And if you would now compute the inner product, then the first one goes very well because you get a 1 and then you get 2 times a half. But we're kind of screwed in the other cases because sadly, the inner product won't be 0. So we have created a list of possibilities, but they're not all orthogonal to the flow. So that's a problem. So the way that we're going to solve this in our weights assignment is these are the weights that we had. And what we're going to do is we're going to change them in the following way. So instead of going from a half to a quarter to an eighth to a 16th, we're going to have a quarter 2 times, and then we're going to have a 16th 2 times, and then we would have 1 64th 2 times, etc. So that's a tiny modification. And let's see how this affects our weight and our energy. So our weights will still be linear, because first we get 2 times a quarter, then we get 4 times a quarter, then we get 8 times a 16th. So we've even made the weight of the graph slightly smaller, so that's good. And if we check the energy, then we know that it's precisely the same as the weights. So this is also linear in n. So that's good. This new weight assignment doesn't kind of ruin our algorithm. And in fact, I claim that it even helps us with the orthogonality of our alternative star states. So remember that the star state is we have 2 kind of star states. We have the star states in a vertex where all the edges coming out have the same weight. And that's actually very easy because we don't have to decide what the parent is. Because as you can see, the state doesn't discriminate what the parent is. It doesn't distinguish what the parent is. There's no different weight on any of the children than compared to the parent. So this case is easy and we can just throw it out. There's no need to make alternative star spaces for these vertices. But of course, the more interesting vertices are the other ones where the weights actually do change from the children compared to the parent. So let's check out the flow again. And now this square root will contain precisely a quarter. So what we'll see is that these 2's will very nicely just fall off. So our flow will just be proportional to, again, just a non-weighted superposition over the parent and the children. And again, we're just going to assume that the parent is U1 and that the children are U2 and U3. And now if we look at the alternative star states with the new weights, you can very nicely just compute these inner products and see that it will be 0 everywhere. So we have now created kind of different star states, but they are still all orthogonal to the flow. And that means that we can just run our phase estimation algorithm. And it will give the complexity that we saw of ON, and which we saw, let me see here, because it will just be the square root of the energy and the weights. So what happened, like what is kind of the big framework that you're doing is you're still using the electric network framework from Beloff's. So you're generating an initial state, you're generating star states, you're computing the energy of a circulation and the weight of a graph. But the big difference is that instead of star states, you'll now be generating star spaces. And you have to really make sure that your circulation on C, that your flow, that it's still orthogonal to all these star spaces. So there's a little bit of more extra work involved, but it does allow you some nice results, such as the welded trees. So to kind of summarize our work, we have extended the electric network framework by Beloff's to allow for both alternative neighborhoods, as well as replacing kind of expensive edges, which could be like a quantum subroutine, by just a path of very simple edges. We've applied this to K-distinctness to get the time upper bound that matches up to polylogarithmic vectors, the query upper bound by Beloff's. And we've also shown how to apply this algorithm to the welded trees problem to get a linear time algorithm for welded trees. That also kind of uses classical intuition instead of relying on Hamiltonians. Yeah, and that's it. And let me know if you have any questions.
Thanks a lot. It's a very nice result, and I think it's very interesting. I like the result, and especially the way it was this protocol is constructed. I don't have immediate question because I have another meetings at 4, so that's why I have to excuse myself. So very nice to meeting you, and hopefully I will see you soon.
Yeah, maybe we'll see each other at QIP.
Yeah.
And
okay.
Thank you for having me.
Okay. And the rest of the team would still be here if they have questions. Okay. Thanks.
Okay. Goodbye.
Bye. Bye.
Is there any question from the audience? Okay. I remember the wheel tree, the decision problem for the wheel tree. The original paper proposed a continuous time quantum walk to resolve this problem, right? Yeah. So I think it's really interesting to use such it's a discrete time quantum walk.
Exactly. Yeah. Yeah, it's funny that you can also just do it kind of in a classical discrete way, which I find, because I mean the original welded trees algorithm with continuous time quantum walk, it's a great paper, and it really showed the kind of first exponential separation with walks. But this this continuous time walks, they're quite hard to apply, and I don't know of any other results where they have been able to kind of use this method to gain any other advantage. These kind of setting up these Hamiltonians are quite hard to do in practice, and I think one may kind of lose sight of what's going on. And I think doing it this way, you can kind of keep a bit more intuition, and at least we've managed to apply it to 2 applications and hopefully more.
Yeah.
By the way, if anyone also has if you ever come up with a question regarding the paper, you can also just email me or Stacey, and we'll also always be happy to discuss it.
I remember there's a exponential separation for the heating time in the hypercube structure. I remember, yeah, there's an article. So maybe your method could also be applied to that case. I remember.
That makes sense. Yeah. That's actually a fun thing to look into. Yeah.
Yeah.
Yeah, and also note that there is still like phased estimation going on in the background. So for instance, in the welded trees problem, we do not actually compute the path. And I think actually it's probably even forgetting the path. It just finds out where the end of the tree is, but we're not like keeping track of the path or something. We're not like storing very nicely all the edges in some registers, and then at the end you have just your whole path, which is what happens classically. So somehow there's still something weird going on under the hood, but yeah, it would be fun to look into it. What's really happening in this welded trees example.
Yeah. And for the cake distinctness, could you explain briefly how do you use your method to obtain these?
Okay, so yeah, okay, so in the K distinctness case, you create a graph.
Yeah.
With different layers. So the first layer, the first kind of vertices would just be, it's kind of like a Johnson graph. So we just have a subset of elements that contain no collision. I would just do the three distinctness. I'll just discuss that case because K distinctness just generalizes that. So in the 3 distinctness case, your first layer of the graph would be a Johnson graph of subsets.
Yeah.
And then your second layer would be you add an extra element that could be like the first part of the 3 collision, and then you add a second element, which would be the second part of your collision, and then the final part would be a 3 collision or not, and those would be the marked vertices or not. That is kind of too expensive to do in a time complexity kind of way. Because you also have to kind of keep track of what the collisions actually are. And if you want to update that, you would have to search through your whole subset of vertices, and that would be way too expensive. And this is something that Belos already noted in his K-distinctness query algorithm. And so he did a kind of a smart way of compressing this. But there is a problem when you compress this, and I won't go into the details, but basically you get the same situation as with the welded trees, that sometimes you'll be in a vertex and you know that there's like a correct edge out of the vertex, but you don't know which one. And it would be too hard to compute which edge to take. And then kind of the same thing as we did here with the welded trees is we'll create some kind of bigger space that kind of contains all possible solutions of edges. And we know that the correct edge is in there. And then we have to show that all these alternative edges are still orthogonal to the flow that flows through the graph. I'm afraid I won't be really able to delve into more details because I'm afraid it would be just a bit confusing and technical without like pictures accompanying it.
It's fine. It's fine.
I would happy to discuss the paper once, maybe like over Teams or Zoom.
Okay, thank you. Okay, is there any further question from the audience? Okay, if there is no further question, thanks Sebastian again. Thank you.
Yeah, thank you for having me. And yeah, maybe we'll see each other at QIP or otherwise QIP next year in Taipei.
Yeah. Hope to see you soon.
Yes. Okay. Bye-bye. See ya.
Bye.
国田
啊，
你可以稍微解释一下他在讲什么？我记得